Thank you all for coming today. Our speaker today is Jim Cox from Sandia National Labs, and I've known Jim for 15 years maybe, since we were both young researchers, and he has done very seminal work in solid mechanics, in modeling interfaces, debonding, and his recent work is in modeling cohesive zone behavior, and he'll be talking to us today about things he's been doing in the area of enrichment. Jim?
So I have to say these things make me a little bit nervous, since Rajay warned me that this could end up on YouTube. I won't mention any names, but a professor at UC Davis was giving a satellite course. I don't know if this is going to go on or not. Can I just stick it in my pocket? Okay. He was giving a satellite course to the national labs, and forgot he was wearing one of these when he was given the exam. And after no one from the national labs appeared to have any questions, he went out in the hallway and forgot he still had it on and broadcasted his session from the bathroom. And so I'll try to remember to take it off so that my session from the bathroom doesn't end up on YouTube. So anyway, so the title here is an analytically enriched finite element method for cohesive modeling. And sorry, I didn't change the title slide, so we'll move on from that quickly. Okay, I'll give a preview here, giving a brief introduction, talking about what's referred to as partition of unity finite element methods, and more specifically for fracture, usually referred to as extended finite element methods. X sounds cooler. We actually have a group at Sandia that meet on this topic of extended finite element methods, so I jokingly refer to it as the X-Men support group, which sounds a lot more macho than calling it the Pooh-Men support group or something, so we do like the X better. Numerical formulations all address some issues that have to do with the solver, give some results for a model problem, talk about extensions for mixed mode, give a few mixed mode examples. When I presented here last, we were mainly trying to demonstrate what it would do in mode 1. So and then this time now I'll show some results for mixed mode and also look at examining the accuracy of the fields, and then with some observations and conclusions. Now, so as a preview on the introduction, first I'm going to introduce the idea of a cohesive crack model, knowing that many times we have diversity in the students in terms of what their background is. And then briefly talk about objective goals and approach and some background in terms of a little bit in the literature, so where this fits in. So first of all, I want to introduce the idea of a process zone. So this is a region where inelastic processes are occurring that lead to a new surface. Now, in particular, we could talk about, for example, concrete, quasi-brittle type material where you have initiation, growth, and coalescence of microcracks. If you're talking about a metal, you might be talking about localized high regions of slip and that lead to void growth and coalescence. So I'll focus more, say, on the civil side today, and show examples that tie to concrete. So linear elastic fracture mechanics assumes that this process zone in 3D could be idealized as a curve, or if in 2D, visualizing it, you would think of it as a point. So we're saying all of the inelastic processes that contribute to creating this surface can be limited to this very small region. So as such, the appropriateness of this really depends not just on the material, but also the scale of the structure. So in a civil example, if you look at concrete and you're talking about beams or typical members in a building or whatever, that process zone size is significant. On the other hand, if you're talking about a concrete dam, the size of it could become relatively small compared to the size of the structure, and so you could apply linear elastic fracture mechanics. So we're going to focus on the case where you can't idealize it as representing a point, and we're going to need to represent this process zone, but we're going to make another assumption, and that is we're going to idealize the process zone as a surface, or in 2D it's going to be represented by a curve. So we're saying all the inelastic processes will occur over this curve in front of what we would think of as the true crack tip where there isn't any bridging. So now there are classical roots to this. If you go back and look in almost any introductory book on fracture mechanics, they'll talk about Barenblatt's work with atomic bond breaking and Dugdale's work accounting for plasticity. So in a sense, it has a long history. Now, numerically, to represent this process zone for a cohesive crack, we'll use the term cohesive zone model. So this assumes the process node can be idealized, as I mentioned earlier, with the cohesive crack assumption. And I'm going to show how we make this assumption, if you will, or the idealizations that are incorporated with this assumption by just looking at the case, say, of concrete, where you have these micro cracks that initiate, grow, and then coalesce. Well, we're going to make some idealizations here and saying, well, we really have something that's more complex. It does have some volume associated with it, but instead we're going to treat it as if it occurs over this surface. So the actual tractions then, which are complex if you get down to a small enough scale, are going to be homogenized to be the tractions that occur on this surface. And the kinematic effects of all these micro cracks are essentially going to be lumped into what happens on this interface. So these two things then, the tractions and the corresponding relative displacements of this surface, are work conjugate terms. And I'm trying to, in this talk, I'm trying not to swamp you a whole lot with equations, but if you looked at the weak form, then they would show up in the weak form as an integration over this surface representing the cohesive crack. Now, as such then, these two things being work conjugate, then we have something analogous to a constitutive model, but here it's not being applied to the continuum, but rather being applied over this surface itself. And we want to have a relationship between these. So the kinematic variables are the relative displacements, and the kinetic variables or force-oriented variables are the tractions on here. And so if I show it just in terms of one traction component and one relative displacement, we'd have the simplest of models is one that has linear softening as this, and the energy under this, because these are work conjugate, the energy represented by the area shown here is the energy required to create a new surface in the body. And so typical number in concrete for normal concrete is about 100 joules per meter squared. I'll show an example later that involves glass, and so you'd be, say, more down in the order of 6 joules per meter squared. Pardon me?
Delta N is the opening?
So delta N represents the relative displacement across this in the region where you still have bridging. Okay, so in other words, this point here, for example, where the crack ends would correspond to this point on this curve. Up here at the very tip is where you've just started into that process. This is what you would think of at this point as the physical crack tip, in the sense that there's no bridging across the crack anymore.
So there's no more singularity.
Right. So in the type of models we're talking about, we don't have the singularity, and I'll come back to that in just a moment when we talk about the enrichment functions. And as you're alluding to in linear elastic fracture mechanics, you do have that singularity in the stress near the tip. So our objective in this work originally, and I'll mention the history in a moment, is a valid means of modeling material localization and finite element analyses. Now this is an international symbol that I use in my presentations. It hasn't quite caught on yet at conferences or anything. This is the international symbol for do not include softening in the constitutive relationship. And the reason you don't want to do that, and that was the simplest thing that was done first in trying to model failure, and we sort of led ourselves down this path, but it leads to pathological mesh dependence. I don't just mean mesh dependence, but something that in the limit gives a nonsensical result. For example, if you take a rod of elements that are, so you're 1 by 1 by 10, for example, and you pull on it, well, I think of this as at the moment as just being linear elastic and linear softening. One element, because of your discretization error, one element will reach that peak first, okay, because we don't have a perfect analysis. And as such, it will tend to soften down the softening curve, whereas all the other elements will unload down the elastic curve. Well, the problem is, now you refine that mesh, okay, double it again and again and again. Each time one element is going to die. The area under that curve would represent the energy per volume that is required to create that crack. Unfortunately, your volume's going to zero, so in the end you get this nonsense result saying it takes no energy to fail this rod. Okay, so that's what I mean by pathological mesh dependence, in the sense that as you perform mesh refinement, you'll get a result that's non-physical. So our goals in coming up with a valid means of modeling material localization were that we wanted it to be applicable to cohesive zone modeling, and therefore we wanted to have a strong discontinuity. So by that I mean that we're going to lump all the localization into this surface, as opposed to, say, for example, a weak discontinuity would have a zone of region that was failing in physical terms. Okay, and we wanted to be able to have a method that could go in any direction, so any arbitrary direction relative to the mesh. There are workarounds to what I mentioned up here in terms of scaling the softening and all, but they still typically have problems with the orientation of the mesh that will determine the crack path significantly. And we wanted to have, for lack of better terms, what I refer to as a continuous discontinuity. And what I mean by that is when the element goes from, when the crack goes from one element to the next, the jump or the opening of that crack will be continuous. So the jump remains continuous from one element to the next. There are methods where that isn't the case as well. It doesn't mean they're invalid because of that, but that was one goal we had. So our approach was to develop an extended finite element method that allows the displacement field to be enriched in the region around the crack. Now there are two things, specifically in using analytical enrichment, there are two things that I'm trying to do. And one is that I'd like to represent the discontinuity without mesh refinement. So we want the basis functions, if you will, of the underlying approximation to include this discontinuity without remeshing to obtain that. And the second is that there's potential for, with analytical enrichment, is to represent the gradients in the vicinity of the crack without mesh refinement as well. Now, I'll mention heaviside enrichment in a minute, and typically you can obtain this with heaviside enrichment, but you're left trying to represent the gradients around the crack just by increasing the mesh density enough to pick it up with the polynomial functions.
What you mean by discontinuity here is different from the standard crack, so it's a cohesive crack.
Yes, so it's a discontinuity in displacement though, except that, yeah, you're right, in the region where we say the crack is cohesive, we do have bridging across that with tractions. But it is still a discontinuity in the displacement field. So.
Is there some mathematical way to distinguish between the two discontinuities? The original one that you have with the usual crack and the one you get with the swing? Are there different degrees of?
Well, to answer the question, is there a way to mathematically describe that? I would say yes. Yeah, I'm sure a mathematician somewhere knows how to mathematically discern the difference. I would say in the context of the weak statement of this problem, there's certainly a difference between them in the sense that we have a term that comes into the weak statement that represents only the cohesive part of that crack. The remainder of the crack simply is a traction-free region of the crack, so it doesn't have the same contribution as it does in that region. Numerically, we also are trying to distinguish, where we have the cohesive part and where we don't, so that we're only performing integrations in the region where we have the cohesion. Now, in terms of the work that this builds upon, I would say the two papers that are key to all of the XFIM type work is, first of all, Malinick and Babushka's paper in 1996 that provides a theory for partition of unity finite element methods. And just in brief, and if you want the full mathematical description of partition of unity, you can look at the paper, but in brief what we're talking about is that there are basis functions when added together, or think at the element level, think of your shape functions, that they have a value of unity at any point within the element, okay, which is necessary for convergence to begin with. And so what we're going to do in these partition of unity methods is we're going to bring in the enrichment or the analytical functions that we use for enrichment in a product form with a partition of unity. It can either be the original basis functions that you were using, or it can be a lower order, but that's the significance of it. Belichko and Black in '99 took the ideas of partition of unity finite element method and extended it for linear elastic fracture mechanics, and they used the term extended finite element method. The main distinction between that and PUFEM is the fact that in using the functions that we do for linear elastic fracture mechanics, we're not just enriching the field, but we're actually introducing a geometry change because these functions have a discontinuity in them. So that's one of the key differences. And it's that term, extended finite element method, that's been referred to the most in the context of fracture. They use asymptotic displacement fields near a crack tip for enrichment. And as Professor Ganem just mentioned, that does have a singularity in it when you're looking at the stress. Yes?
We also have done enrichment before discussing in the context of the sum. Partition of unity, right?
Yeah.
What does the partition of unity bring to?
Okay, first of all, you automatically get the continuity that you need and within the elements in terms of, or between elements, because you're multiplying it by the corresponding shape functions. But the other aspect is that you maintain the properties that we've come to all know and love in terms of finite elements, in terms of having a sparse matrix for the representation, say, of a tangent stiffness or sensitivities and all. And you maintain that same sort of property because you're bringing it in a product form. So numerically, there are many aspects of it that carry over that we're used to with normal finite elements. Okay, XFIM, PUFIM, cohesive zone studies. So we started this work back in 2001 before the paper of Wells and Slice came out. And well, we actually started in 2000. And our intention was to try to come up with a way of enriching the cohesive crack problem and not the linear, I don't know why this goes into autopilot, but linear elastic fracture mechanics. And so there have been several papers that have come out since then in cohesive zone studies. And the first, Wells and Slice and Mose and Belichko, were, I would say the work was done rather concurrently, but in both of those, they're using heaviside enrichment to represent the crack. And then Xi and Belichko looked at, say, a way of addressing a tip propagating through an element, which in these previous two cases you couldn't do. It went from element edge to element edge. The work that's closest to what we're doing is Zhao and Karihalu, where in 2006 they published some work on using what they refer to as asymptotic fields for the enrichment. And so the work we did was, I would say, concurrent with that of Zhao and Karihalu. And both of us used something that people have referred to as asymptotic fields. I think the term is, I'm not a mathematician, but the term is a little bit questionable in the sense that in these cases, say, unlike linear elastic fracture mechanics, or often you're talking about something in the limit as you go to infinity when you're talking about radiation boundary conditions or something of that nature. In this case, when you approach the cohesive crack, one term alone does not dominate. So that's why I tend to question the terminology of the use of asymptotic fields. Furthermore, we don't have the same asymptotic fields that we're using. So anyway, and then another related thing for students that might be interested in this is the generalized finite element method is built upon the PUFIM as well. So you'll see all three of these in the literature. In brief, there's many other efforts at Sandia Lab. I'm certainly not the only person involved in XFIM related work, and there's several other efforts that have been involved. And these up here represent talks that for an organized seminar series that we had on extended or enriched finite element methods, and then more recent work has addressed implementing these in what I refer to as Sierra mechanics codes, solid mechanics and fluid mechanics. Sierra mechanics is our, say, a framework for doing multi-physics codes at Sandia. It's really our production type codes. Now, I'm going to give a real quick overview of the history, just to note that this work actually started when I was at a visiting researcher at the Army Research Laboratory. And their interest was in localization in both armor and in penetrators. So maybe the nature of the localization, for example, may have been more in the area of an adiabatic shear band or whatever, but still they needed that type of modeling capability. And so in this context, we started this and came up with a general formulation and algorithms. And at Sandia National Labs, we've extended the work. I'll talk about several of these items today. The work that's in progress right now is looking at the applicability of these enrichment functions to other classes of problems, meaning problems that don't satisfy purely the case of being linear, isotropic, homogeneous, elastic domains, extending it to formulations for finite deformations and also implementation in production codes now. So I've been using the term enriched methods. Let me start off. We can either look at this at a global or an element level, but let me just use element as an example. So our displacement field in a typical or standard finite element method is one of having these shape functions typically obtained as polynomials multiplied by the corresponding nodal displacements, okay? And in PUFIM or XFIM type methods, the extension that we make here is that in addition to these terms, we add in some terms where we have these enrichment functions multiplied by shape functions. The notation is a little weak here. We could constrain this so that it was okay, but in some cases this is not, we could call this n sub n bar and have this represent a different set of shape functions here, still a partition of unity, but for example you might use quadratic shape functions for this and you might use bilinear over here. Now, In general, you could still use this equation by constraining your alphas, but it'd probably be more explicit to indicate that they can be different. So as such, we bring it in this product form. For fracture mechanics, then, the idea is as the crack propagates through your domain, there's going to be specific nodes that you bring in these enrichment terms in on the fly as it cuts through the domain. And there's different schemes for determining which nodes you're going to do. The one that's depicted in this cartoon here, if you will, is that any time that we've intersected the support of a particular global basis function, then enrichment gets turned on and it enriches all of the elements adjacent to that or the support of that node. Okay. So we'll touch base on other ideas that have to do with that. Now in concept, the idea here is, let's say for example that you're starting with a finite element approximation and you want to improve upon that. So for the moment, back off, if you will, thinking in terms of the crack problem, and just think of a problem where you want to incorporate enrichment. It could be, for example, a reentrant corner in a domain. Well, the way that we're going to improve upon that in finite element methods is through mesh refinement. So we add an additional set of basis functions through the mesh refinement. And this error E1 now is going to be less than that shown earlier when you had a smaller dimension space. Now you can take these concepts and apply them in the context of the crack problem as well, but then we have to talk about how we're refining this to deal with the crack, so we can think outside of the crack problem at the moment. Now in contrast, the idea here in PUFEM approximation is that we're adding in now, instead of additional basis functions, by adding more nodes to the problem, we're actually adding in additional terms that come in this product form with these enrichment functions multiplied by the basis function. So the underlying idea is that if these analytically derived functions are representative, at least in some region, of what's going on, that they give us more bang for the buck, if you will, in representing this. And then in concept, then the error E2 will be different than the error E1, or will be less, considerably less, for considerably less degrees of freedom. So that's sort of the underlying philosophy behind what we're trying to do. Now, the question is, what do we use for the enrichment? And first I wanted to show what's done in linear elastic fracture mechanics. And this represents one of the terms that would be used for enrichment in linear elastic fracture mechanics. And of course, U2 has a square root of R variation, which means, of course, that this, then if we look at a gradient term of that, we're going to have a 1 over square root of R singularity in the problem. So this is what was used, say, in the paper that I mentioned, Malichko's et al.'s early paper on linear elastic fracture mechanics. In the wake of the crack, they later determined that it was useful to switch over to a heavy side, both in terms of, well, partly in terms of the number of degrees of freedom that are associated with the enrichment now, and you could just go to a simpler thing. Now, on the other hand, this was what also was first used for cohesive crack problem, and you'll notice that it doesn't have a plot over here because the zero plot's sort of boring, but if we look at the gradient of this, we end up with nothing, right? So this enrichment function doesn't contribute to the gradient around the crack. Rather, you have to pick that up, as I mentioned earlier, through having sufficiently fine polynomials.
You have to know where to enrich, right?
Yes, yes.
You enrich in areas where you're not needed. You get 0 coefficient for enrichment or very small coefficient.
There are a few different problems. If you enrich too far away and your function is becoming almost constant in those regions, you can also have issues with regard to singularity in the matrix as well. But yes, so one of the things you want to do is to enrich where it's going to help you in terms of the gradients and not in other places.
All around the crack?
Yeah, so we'll do that all around the crack. And with regard to your question, that's part of the motivation for switching to the heavy side in the wake of the crack behind it, is that the other enrichment functions, I mean, one of the motivations is they're not helping you with regard to accuracy anymore, so why pay for them? So, and there's another issue that I'll mention in a slide in a moment, and that is in our particular function that I'm going to show, there's a length scale. I maybe shouldn't even use the term length scale, but there's a length parameter associated with the solution, which is the length of the cohesive zone. Yet that's something we don't really know ahead of time. That's a function of the boundary value problem. And as such, then, it would make sense that the region that we're going to enrich is actually tied to that length. And so I'll mention neighborhood enrichment in a minute in terms of determining how to enrich. Now, I tried to take some encouragement. This is my path to enrichment, so I thought that would be appropriate in California, you know. So I tried to take some encouragement from one of the earliest, what we might call a Department of Energy researchers, you know, one of my early predecessors in DOE, Thomas Edison. For example, the second one, I have not failed, I've found 10,000 ways that won't work. Okay, now, we spent a lot of time trying to come up with enrichment functions that would be useful. I won't claim certainly that what we did was anywhere near as profound as the incandescent light bulb, but at the same time, I did relate to that with some of the early efforts we had. These show, for example, some rather ad hoc functions that we obtained that had the nature of the solution that we wanted. But in the end, what we ended up using is really enrichment functions that come from analytical derivations based upon the Mushkela-Vili formalism. Now, I don't know about you as students, but when I was in elasticity theory as a student, I was always hoping we wouldn't get to that chapter in the book, and we really didn't when I took it. And so, and plus, you know, you guys, you love to use your computers, but maybe you don't like to do complex variables as much, and that's the downside of this. So anyway, there are two different sources. I shouldn't use my long arms so much, I guess, but two different sources, Hong and Kim and Zhang and Ding, that had work that we built upon, first verifying proposed solutions, but especially in the case of Hong and Kim, which was really focused on the inverse problem. It's going to stay on. Yeah. There's a fair amount of work in taking the analytical work that they had done and coming up with enrichment functions that can be used for the crack problem. And all of them, as I mentioned, are based upon the Mushkela-Vili formalism, which writes the displacement field as a complex field in terms of two analytic functions. In the case of the crack problem, they're analytic over all of the domain except where the crack is. So you have to come up with an expression for these. In general, they use series type solutions in both works. The reason that we were interested in doing this is that I initially examined the solution that you would get from just the first terms of these series solutions in Hong and Kim and compared them with a very fine scale finite element model of a model problem that I'll show in a minute. And you can see that the field for, this is sigma 2,2, the field looks very similar. Now keep in mind that they're not scaled the same. The red region here represents the length of the cohesive zone, but at least it suggests that if you were to use the underlying displacement fields from this analytical work as part of your basis to represent the field over here, that it's potentially going to help us and not require us to use nearest fine of a mesh. I would mention here again that the cohesive zone length is 2c here, as that's what we're normalizing by as the value c. So the actual length of the cohesive zone is twice that. Okay, now in the work of Zhang and Ding, they used conformal mapping, i.e. elliptic coordinates. You can think in the limit that if this were actually linear elastic fracture mechanic, this cohesive zone would shrink down to a point and you just have a typical polar coordinate system around that point, okay? So essentially now we're taking the geometry of the crack, stretching it out and having a coordinate system that conforms to that, if you will. And as such, you can relate the coordinates of a point in the domain as a complex variable in terms of its elliptic coordinates in the domain. And you can, with a little bit of screaming and gnashing of teeth, you can work your way backwards to have the inverse relationship, which you're going to need if you're going to do numerical integrations on basis functions that have products from this. So one big difference between the work of Zhang and Ding, at least for us numerically, was that they adopt a Westergaard stress function. So the lowest order terms only have one unknown analytic function. And so you have half as many terms when you start using enrichment for a given order. So that's a little bit convenient. Now the solution, as I mentioned earlier, is expressed as a series, and what I'm showing you today only includes the one term, and it's what they refer to in their work as being the asymptotic solution for this problem. So rather than show a bunch of equations and ask you to visualize those in your mind, I'll real briefly show some figures that reflect the nature, at least I think I will. Sorry for the delay. I'm sort of an amateur underwater photographer, as Professor Ganem mentioned, so I get real greedy on resolution even if I don't need it for the output device. So here's U2 and U1, the two components of displacement. You can see this one. This is for mode 1, and you can see that it represents the crack, the jump in the crack here. And likewise, sigma 2,2 is similar as to depicted in that previous plot, but that was with the Hong and Kim stuff, that you see a very similar response for sigma 2,2 and sigma 1,1 here as well. So we're going to use functions of this sort for our enrichment around the crack.
What is the exact point of these basis functions?
Okay.
Satisfy?
So they're derived for a linear, elastic, isotropic, homogeneous domain. And so you could use the basis functions to satisfy different boundary conditions for this problem, but in particular you could adjust them to try to match what you get for the separation and the traction at the interface. In a sense, when we just choose one term, we're not taking it to that full extent, although that's a possibility. And your question is a good question also, because when we get near the edge of a domain, which we're not, with one term of course we're not trying to satisfy that boundary condition of a free edge when we approach it, that we're also not going to do as well in that region either. So it's a good question. So I wanted to just mention that Professor Ganem previously asked how do we decide what region we're going to enrich, and that's an excellent question. I jokingly refer to this as Mr. Rogers modification. I don't know, many of you didn't grow up in the U.S., so I don't know if you had Mr. Rogers exported to you or not. But anyway, I thought anything that's enriching a neighborhood should pay tribute to Mr. Rogers. But anyway, so that hasn't caught on at conferences either. No one else is using that. Anyway, so what I'm showing here is the idea of how you would enrich a region. And in particular, I mentioned earlier, you might switch over to Heaviside functions. Well, I'm denoting that with S for step and using a T here for tip enrichment. So for example, in linear elastic fracture mechanics or the cohesive crack modeling, you'll have some region that you would use the analytical functions and you might use a step. But in terms of, in this case, I'm just showing the intersect type enrichment, but one could also define a radius over which you use the tip enrichment in a greater region, okay? And there's motivation for that, certainly. If your polynomial functions aren't representing sufficiently the gradients around the crack, but the enrichment functions are for a certain radius, then we should be incorporating the basis over a larger region. And there's certainly been significant work on this in the literature as well, including some in linear elastic fracture mechanics showing that if you want the optimum convergence rates, it's helpful to have a certain region defined and not have that change with mesh refinement. Now there are many issues in the numerical formulation. We'll skip them today for the most part. I'm going to mention a couple related to the solver. And one is that as we're adding this enrichment with the crack propagation, we're adding new degrees of freedom on the fly. The problem is they don't have good initial values because they didn't exist before. And so the nonlinear solver can tend to croak on this type of thing. And I've had cases where I'm trying to run it and these new degrees of freedom just completely ruin your convergence until eventually, based on the parameters you put in, it'll say it can't get there. So a solution that I've come up with for when I was doing this with relatively coarse meshes is what I refer to as penalty relaxation. Typically in penalty methods, you're thinking of using a penalty addition. Say if you think in terms of some functional to your problem, you're bringing in a constraint that you want with some penalty parameter, and as you make that penalty parameter greater and greater, you satisfy the constraint in a more rigid way, or more consistent way. So in this case, we're actually trying to do the opposite. We're trying to initially take the new degrees of freedom, penalize them to be 0 because they simply didn't exist before. We didn't have enrichment of those nodes. And then relax that penalty parameter, and then in the end having it be 0, i.e. you haven't penalized them. The advantage to this type of thing is that, say for example, we're using a Newton-Raphson solver where we can actually see quadratic convergence. If you do this type of thing and you relax that penalty parameter in the correct way, you have a series of smaller problems, if you will, in the context of a multi-level solver, but you're getting quadratic convergence for each as opposed to suffering through linear convergence for a solver that was really designed for quadratic. Now the other item that I mentioned here is that it seems to be physical at first, but it's not purely physical. I mean, well, let me put it this way. It has an effect on the numerics, and that is for quasi-statics, stress relief should occur between the cracks. That is, if we're doing a problem at relatively slow loading, the unloading that occurs due to one crack opening should affect whether another crack develops or not. It affect the stress state in that region. Okay, and if you don't bring this in, you can end up with very non-physical results, and they can yield numerical problems, as I'll show in a moment. So the solution here is to compete all cracks that satisfy the criterion of initiation or propagation, and only advance the winner. And by what I mean by that is to have a criterion, let's say for example that F has to be 1 or greater for the crack to initiate or propagate. Well, you find the one that has the largest value of F to determine which one you're initially going to let crack. Once you do that, then you go ahead and solve that problem. You go back and you say, okay, are any of the other candidates or any new candidates still satisfying the criterion? So you have to go through and loop through those, but they're each based upon an equilibrium solution.
So now we're talking about crack initiation
Yes.
as opposed to propagation.
Yes.
Right?
So typically in the context of a cohesive crack formulation, it doesn't have to be this way, but we're going to use the same criterion in what I'm showing you for both. And if you didn't have the same criterion for both, then yeah, you do have the issue as to how to weigh one versus the other in terms of satisfaction or not satisfaction of it. But in this case, for example, the problems I'll show today, it will be when your tensile strength exceeds, your maximum principal stress exceeds the tensile strength or a fraction thereof. Now, in terms of what those two things that I mentioned look like in the context of a solver, and this is sort of, well, my old code uses a pseudocode input for defining how the algorithm works. So the gray here depicts the time-stepping loop. This depicts the solver loop. And for these smaller problems, I'm using the Newton-Raphson solver. The purple here depicts the region where we're what I call the localization loop, or the loop over which we're deciding if another crack advancement should occur. This over here depicts, say, my model problem I'll show in a minute. In this area, for example, you can see that one crack arrested the other. This one isn't continuing to grow because it's being arrested by the crack adjacent to it. Now, this sounds like, well, I thought it was a relatively straightforward thing. It's something I would expect to be in a lot of codes. However, on the commercial code side, one example of XFIM right now exists in Abacus. And I'll briefly show you an example of why that type of thing is important, and I would say from the results we can infer that they haven't incorporated that type of thing in the Abacus code yet. This is the penalty reduction loop that I mentioned earlier that's basically trying to help our solver maintain optimal convergence rates. Now this is an example of a glass fiber. This is a fiber optic, and the region around it, this cone shape, is glass solder being used to seal this fiber in a package. So we have a package for a small device that we have this fiber coming out of. We're using this glass solder to seal it with the surrounding package, and we're hoping this will maintain a hermetic seal between the package and the outside environment. So we're interested in this not cracking. Well, in this case, when we ran this initial 3D analysis, the first set of cracks we get in the context of Abacus are these. They sort of look like turbine blades around an axle, right? So we not only have three regions where the crack started to initiate, but because of the definition of this problem having symmetry, and you can actually see the cracks on the surface right here of this real thin layer, because of the symmetry that we used in the modeling, the fact that we're treating everything homogeneous, and Professor Gannon would, be the first to say that's all a lie, and I agree, but because of these idealizations, we end up with this sort of radial deck of cards around each of these regions, because all of them are reaching, within the given time step, they're all reaching the criterion for initiating at the same time. However, this isn't necessarily physical. So let's look at this in 2D. I'm just going to take a plane strain slice, and the previous one I showed you was like if you countersunk the hole for putting more glass around it. So countersunk with a cone shape. So now let's say that we're doing one where we just have a cylindrical countersink here, and we're just taking a plane strain slice of this. The mesh here is that of the fiber. This is glass solder around this, and this is the representation of the region of the package out here. So we take this thing up, and I didn't describe it earlier. So we're coming down from, say, the glass transition temperature, we're cooling down from that point. And so all we're doing here is looking at a problem that's isothermal. We're slowly bringing it down, and we're looking at what happens in terms of whether we're going to crack the glass solder as we cool this down. So here's the first analysis, okay? all these new lines out here are not mesh refinement. There's only 2 elements that radially didn't crack all the way through, okay? So it's the same sort of thing we saw in 3D. We get this radial deck of cards, if you will, going out. And that's because it appears that when this first cracks initially, all these elements in that first ring there, except for 2 of them, reach the criterion of initiation. They don't compete them, and so you'll have all of those cracking. Now, if you're competing them in this context, the only difference is going to be due to your discretization. I mean, we don't have perfectly symmetric meshing here, for example, for this fiber. So you're going to have some places that are just a little bit higher principal stress than others. But if you did compete them, you would tend to get one dominant stress that initially it inserted, and then progress to see if more needed to fail. This is the second take on the analysis. You can see it looks a little bit different. If we zoom in on this, you can see what happened is you still crack many, many elements, but in this case you weren't fortunate enough, if you want to call it that, for them to all propagate radially outward. Rather, they ran into each other, and then eventually the algorithm dies, I guess in part because of this condition. There's different things you have to do when you have intersecting cracks than if you don't have intersecting cracks, and so the analysis does not succeed at this point. So, originally I didn't put too much emphasis on that, but I just wanted to mention that at least in the version of Abacus that exists up through today, and my understanding is there's a new version coming out in May, so these things may be addressed in the new version. But be aware that if you try to use that there are some things you have to be very careful of. In that previous problem that I was just showing, just to close on that, if you move the fiber just off center, then you create a little bit of gradient, and that's realistic. We're not going to place that fiber perfectly in the middle. And if you do that, you will get one crack to initiate. The problem is as you refine the mesh, still in that region that is hotter, eventually as you refine the mesh, you will go back to getting 4 or 5 cracks, and they'll run into each other, and you'll have a problem again. So anyway, now I'm going to present results now for using the general methodology that I've discussed briefly here, and the emphasis here is on reproducing the crack history in the first result. So we're going to look at the history of the crack tip and the cohesive crack tip as they go across the domain. Then we'll go to extensions for mixed mode, give mixed mode examples, and talk about the accuracy of the fields in the problem. Now, I would mention here that all the problems I'm presenting today are for a quasi-brittle idealization. That is, the material outside of the crack itself is treated as elastic, but we're going to have a cohesive crack that has a finite length. So the interest initially is to see if the enrichment will even work for the class of problems, as you asked earlier, and see if it will work for the class of problems that correspond to the analytical solution, and that would be a quasi-brittle type problem. Now, the first example I'm showing here is for concrete. It originally started off as some sort of aluminum when I was at the Army Research Lab, so you change your problem to make your sponsor happy. So the initial work at Sandia Labs was looking at hardened, deeply buried type stuff, so they were interested in concrete structures that were very deep and what would happen when due to an explosion, it saw a load from the surface. So the process zone size on this is on the order of 1/4 of the thickness of the domain. And the properties that I'm going to use here, as I mentioned earlier, they're representative of concrete tensile properties. If you really looked at experimental results, you'd want to use some sort of exponential or rational function for denoting this softening. But here we're trying to compare one numerical analysis to another, so we just want to have some qualitatively meaningful results. Again, it's a mode 1 quasi-static crack propagation. The boundary conditions here are such that initially the displacements make this look like pure bending, followed by incremental axial displacement from this point on. And the intent here is to have a portion of the time history where the size of the cohesive zone is fairly constant. Now, we don't have an exact solution, so we're going to use a finite element mesh that has interface elements included a priori down the center of this domain. And we're going to use this as our reference solution. Then we're going to compare XFIM results for meshes that are aligned, so the coordinate directions of the elements are aligned with the crack orientation, and then we're going to somewhat in a contrived way rotate the middle of this domain to be at 45 degrees and see if we get reasonable results for that as well. So I wanted to first introduce, very quickly I guess, introduce the idea again, reiterate the idea of how we're doing this. So this shows a fine scale solution for U sub x. So again, this is with the 80 by 81 mesh. This shows a solution for sigma x that you've seen before. And the way that I noted earlier that we're able to obtain this type of response in the XFIM is by incorporating the enrichment terms. So
Are the enrichment terms for the cohesive thing or for the real discontinuity?
So they're trying to bring in the discontinuity, but they're also trying to bring in the gradients around that discontinuity.
But the gradients that you bring in, they are the analytical solution.
They're both. We get some from the polynomials there, and we get some from the analytical solution as well. But keep in mind that it's being done in the context of a Galerkin finite element method, so it's able to use those analytical, function terms in product with the shape functions in the way that it considers best. Okay, so they're not just applied and say, directly, so to speak. So in this case, I'm showing a 5x5 mesh, and what I'm showing here up in this top figure is the results for this region corresponding to one element, but done with that extremely fine mesh that I showed you earlier. And this is qualitatively what we get for UX in this region. Now at the same time, if we actually solve the problem with the XFIM, and if we look at the response in this one element alone, this is the result we get. So this is 1 by 1. If this were a uniform mesh, which it's not, it's actually graded towards the middle, but this would be 16 by 16, so you'd be 256 elements versus what we get from one. And you can see qualitatively we're able to represent the response, in this case with lots of polynomials, in this case by bringing in the analytical enrichment. Now, we did this, again, as I mentioned earlier, by bringing in the contributions for these bilinear shape functions, but then in addition to that, bringing in the enrichment. And you can see in this case, lambda 1, at least for this element, doesn't exhibit the discontinuity, but lambda 2 does. And you can see that each of the terms here has the discontinuity shown in them. The field that we just showed on the previous page is the combination of all these added together. So it's the enrichment that brings in the portion representing the gradients around the crack for the most part, although the polynomial contributes as well. So in this figure, I'm showing the results that we obtained in the study for that model problem. We have a reference solution depicted in blue. The dotted line represents the actual cohesive crack tip as a function of time. In other words, its position coming through the thickness of the member. This represents the depth of that member. And then likewise, the solid blue line represents the reference solution for the actual crack tip, or the cohesion-free crack tip. The distance between them at a given time represents the length of the cohesive zone. And then in a similar manner, I'm showing two results here for XFIM. One of them switched over to heavy side in the wake of the crack, and the other one did not. The difference at a given time between this reference solution and our approximate solution I refer to as the deviation in the crack tip position. And one measure that I use then to determine how well we're doing over this region where the cohesive zone length is pretty much constant, is that we'll look at the average deviation over a certain time here away from the edges. Your question earlier about what problem we're solving, you can see that this reflects the fact that we're not solving the problem near the edge, because we don't do as well near the edge. Okay. And another thing that you notice here that's a numerical attribute is you tend to get an arrestment of the crack at element edges. The grid here represents the element size, and you tend to get an arrestment of cracks at those edges. And just for the students, what's the nature of our stress field for a displacement-based finite element method? Is it continuous across elements? Well, displacement is, but are the first derivatives necessarily continuous across elements? No, they're not, and that's part of the issue with the arrestment, is that we have a stress field. Of course, you get to not think in those terms because the post-processors clean up all of our mess and make it look so beautiful, but we have a stress field that's not continuous. Okay, now you can see improvement here. I'm running short on time, so I'm going to go through this a little quickly. But you can see improvement here. Not all of it is due to mesh refinement going 9 to 17, but also is that we have this parameter that we call C back in our analytical solution that ties to the length of the cohesive zone, and as you change this, it will change the results, which suggests that maybe in the most formal implementation of this, you would want to have this being changed by the numerical method. And you can see here, this shows crack profiles at different times. Again, we do well overall, but we have more errors we get near that edge. This result here is depicting, I see 1, 2, 3, 4. Okay, so this is for a skewed mesh, and you can see here again we have edge arrestment as well. deviation, though, keep in mind this deviation of 26 millimeters, relative to the depth of the member, that's at 1,000 millimeters, you're still on the order of a couple percent. Again, so for the skewed mesh, we get reasonable results as well. Here we're showing results for the skewed mesh again, 8 and 16 meshes, and you can see that we get deviations of 15 millimeters and 11 millimeters out of 1,000, so you're on the order of 1 to 2% error for that problem as well. If I summarize the results in the table for the aligned mesh and the skewed mesh, you can see that, if you look at the results for the 32 and 33, that we're both down to just below 1% error, and nominally the same thing, so there isn't that strong of a dependence on the mesh alignment. You'll also notice here as you go from 9 by 9 to 17 by 17, there isn't that much improvement. And this ties back to the thing that I mentioned earlier in terms of what you're enriching. You have two things working against each other here. You'd normally think that with the mesh refinement you'll start seeing considerable improvement, but the problem here is that in this case you're refining the mesh, so you're getting more polynomials, but if you're doing it only based upon intersect, you're getting a smaller and smaller region over which you're applying the enrichment. So that's not helping you, whereas the mesh refinement is. Now, for time's sake, I'm just going to mention real quickly that we use a method based on least squares of a neighborhood of a point that we're trying to examine the stress. Especially for mixed mode, we're going to use a method for smoothing out the crack field. This is something that's quite common in the literature, where we use a neighborhood of Gauss points surrounding the crack tip to come up with a polynomial representation. And for time's sake, I won't go through that. Another issue that comes in here is that we have a discontinuity, as we talked about earlier, we have it between elements. Well, we also have a discontinuity in the stress field between the cohesive zone and between the continuum. And as such, we tend to weaken the criterion for when to initiate a crack below the tensile strength. So the next results I'm going to show after this are for the mixed mode problem, but initially we take a mesh that's not regular, so to speak, and look back at our model problem to see, yes, we can get it to propagate across that and give a mode 1 crack that's fairly straight. If we look at the model problem with the smoothing, you'll see that for the 17 by 17, we actually end up with a deviation when we include the smoothing that corresponds to about 1 mesh refinement better than what we had before. It's particularly important for mixed mode, though, because it also affects crack direction. This shows the functions for mode 2 that we're going to incorporate for doing mixed mode problems. So we have the mode 1 and the mode 2 asymptotic solutions incorporated. Apologize, I must have been greedy on my graphics on the next one. Okay, so this is a problem that we're going to look at real quick, and we're just going to look at the ability to produce the similar crack directions. To be honest, the experimental results did not have information on fracture energy, so I'm in good company when I say that we didn't even come close on predicting the load. But if you took the cracks that were produced by that one specimen and make a green shaded region that would contain all of them on both the front and the back of the surface, that's what the green depicts here. And you can see the solid line is what we obtained, the dashed line is what Meschke and Doomstorff obtained. Another XFIM analysis, and in some ways we're complementary of each other in the sense that in their analysis they only used heaviside enrichment, but they used higher order polynomials. In our case, we used just bilinear elements, but we used enrichment to bring in the response around the crack. And you can see that in force displacement sense that we're very similar to the results they obtained, but albeit with relatively low order elements compared to what they were using. So the next slide shows if we change some of the smoothing parameters that I mentioned before, we'll get some deviation in the crack path, but it's still the difference between them is relatively small compared to what we might call the experimental scatter, even though it was just from one test. Another example that we looked at was this single notch specimen. As you'll see, this is a relatively coarse mesh compared to what other people have tended to use, that we're using heaviside enrichment. The next figure here depicts the crack path that we see in this specimen. I don't want to make too strong of a statement here because we certainly weren't trying to see how coarse of a mesh each of these could use, but it is safe to say that finer meshes have been used to solve this problem when they're using a different type of enrichment. So this is with heaviside enrichment, and you can see that they're using relatively small elements, which, in some sense you would expect because you need to pick up the gradients around the crack with the polynomials as opposed to the enrichment. There are other examples in the literature, for example, on people solving this with non-local formulations, and likewise they had to do relatively small meshes. And we started a tad late. How many minutes are we at right now? Huh? Okay. So at this point we wanted to come back and analyze, in part because we wanted to say what happens if we do a different class of problems like an orthotropic material. So we wanted to come back and look at this initial test problem a little bit. And the problem here is that we really don't have an exact solution that we're going to use, in part because we have Poisson's ratio that's non-zero, and we're pulling along these edges under displacement boundary conditions. They're not rollered vertically, they're actually fixed. And so Poisson's effect will give us some issues around the corners here, and so we won't have an exact solution. So we wanted to go back and first say let nu equal 0, and let's just look at, this says here exclude the crack. First we're going to just look at and make sure, first of all, that we're doing the calculations correct for looking at convergence. And this is a 0 Sobolev norm, so has first zero Sobolev norm, so it does not include the first derivatives. So think of it as an L2 norm of the displacement field. And you can see for nu equals 0, we're getting the optimal convergence rate we would expect for these elements, which is second order convergence nominally. Okay. Now if we go to using that approximate reference solution, you can see that we start to deviate more, of course, as we come down towards finer and finer meshes, because eventually the fine mesh actually exists on this somewhere down here. Okay. And so we're going to have the greatest deviation down here. Again, at least it's certainly reflecting that we're getting second order convergence. We're not trying to do anything from the 0.07 except that we're going to be less accurate when we use an approximate reference solution. Now if you go to 0.17, our results give something even greater with a greater difference from 2.27, but still reflecting that we have quadratic convergence. So we wanted to look at that first, and then we move to the crack problem, which is more interesting. And so this is for the case of the crack propagating halfway across the domain, and we're looking at the relative error again in the displacement field for this problem. Now keep in mind that this is only a 5 by 5 mesh, and so the interesting thing is that we're actually obtaining a better result than we did for the bending problem with this relatively coarse mesh. And that was originally one of our hopes, is that we could go with relatively coarse meshes that pick up the global response and use the enrichment to pick up what's happening around the crack. In other words, without needing to put in extremely fine meshes near the crack. If you refine the mesh once here, then you're down to about 0.8% error, or just slightly worse error than what we originally had in the bending problem. And if you zoom in right around the crack and only do this norm measure in this area, you'll be up to about 1.1%. My interest here was saying, well, is the rest of the domain helping us out so that our error measure doesn't exactly tell us how good we're doing around the crack? But you can see they're very similar orders of magnitude, so it suggests that we're doing well around the crack. In this other refinement, however, we're not doing near as well. And this is for known reasons. In this earlier work, we hadn't addressed the issue of blending elements when you transition from an enriched region to a non-enriched region. It's well documented in the literature. I think it was Babuska and Chesa that had a paper on this, and then there have been other examples of how to overcome this in the literature. And so in this example, we're going to lose convergence. We're not going to continue to show quadratic convergence because of that. The other issue that comes into play here is that we're not enriching the same region as we refine the mesh. The region that we enrich becomes smaller as well. And this suggests that enrichment was actually working well, but now we're applying it over a smaller area. So these are things that we will return to, but we're in the process of actually trying to move this stuff to a different code, and we'll address it in those codes. The other thing that we wanted to look at, for example, is if we look at an orthotropic material, can we still use this solution that's based upon isotropy and get reasonable results? And this is a bit of a contrived problem. It's the same problem you showed a minute ago, except that we changed the modulus of elasticities for principal axes of the material. We align them for the x and the y directions as well. This represents the isotropic case here, and of course you expect secondary variables to be less accurate than primary variables, i.e. the displacements. And these are gradients of the displacement up here. And so this is the isotropic result. You can see as we change to 80% and 60% for E1 versus E2, and then going the other direction, that our error does increase. So one of the positive things here is that we're really happy that for the isotropic solution that was the best one, since that's what the analytical solution corresponds to. But you see an increase in it, but I would say, you know, it doesn't increase so quickly that we would be hesitant to use it for all problems that include anisotropy. But at the same time, this is showing one case. The other one that we don't have all the results finished on yet is the case where we rotate these material axes at 45. That's a bit more of a critical problem. We're going to have to cheat and make the crack still go in our path, because it's probably not the path it wants to take anymore, but we want to use the reference solution that we obtained putting in interface elements ahead of time. So anyway, it does suggest that it's still useful. The ongoing work is taking the same ideas and extending them to finite deformations. Among the things that you have to deal with are the fact that when we're using small strain theory, of course, we could just think of the crack as being straight within our element, even for the 4-node quad element and all. But now when we go to finite deformations, what was a straight crack in this reference configuration becomes curved when it's considerably deformed, so we're going to have to account for that. But you can do that by looking at the deformation gradient on 2 points that were initially coincident here in this reference configuration. So we have ongoing work in that, and for time's sake we'll shoot through these quick. I'll start with some of the negative, or well, they're negative but truthful, and that is there's no free lunch. The algorithm complexity certainly goes up when you bring in enrichment, especially analytical enrichment is more difficult than the heavy-side enrichment. There are several open issues, but also opportunities. I mentioned the fact that we find that C, not even being half the length of the actual cohesive crack, gives better results if it doesn't correspond to the actual length of the cohesive crack, and there's reasons for that when you're using just one term. And but there are also questions that we have in terms of how useful is this for other problems outside of an isotropic elastic domain, homogeneous as well. And certainly the first results we looked at for an orthotropic elastic don't preclude its application, but we need to look at other orientations for the principal axes of the material. But at the same time, we'd say it's clearly not the best approach for all classes of problems. We can say that from the onset. There are going to be problems where heavy side is a better method to use because of its efficiency, and maybe because you have to go extremely fine in your meshing anyway to capture the state dependency of the material. Where's Professor Ganem? I put this in here for him. Okay, so the other one is there's really an opportunity here as well, and these methods facilitate stochastic finite element analysis of fracture, in part because you can make one mesh and then you could introduce different defects, different realizations of defects with just that single mesh without needing to remesh for each one of them. And it appears to allow relatively coarse meshes in some cases. If you think of the 5x5 one, we're able to do as well as the error we obtained just with bending by introducing the analytical enrichment to represent around the crack. Refinements are certainly still needed to improve the accuracy, as I mentioned when showing the rate of convergence no longer looking quadratic. And analytically enriched XFIM for cohesive zone modeling of localization at least has potential. It needs more work, it needs more examination, but we think there are classes of problems that would be best suited towards. So the work is funded primarily by Sandia. It started at ARL, but most of the funding has come through the Engineering Science Research Foundations. And I have two different questions slides depending on how difficult your question is. This is the one for simpler questions, and this is the one for more difficult questions. So that's the conclusion of the talk. Yes?
Do you think you could assess question of the kind of running with anisotropic material? Because you moved from, you